the quantitative aspects of describing any interactions, like the kinetics, thermodynamics, enthalpy, entropies, delta G, and so on and so forth. Okay. All right. Okay. So let me phrase the question. So what are the most pressing questions that limit our understanding of how GAGs bind proteins? Okay. So I think Umesh gave he was talking about a system which is extremely well characterized. Okay, I would call what is called a model system. Okay, so there's a lot of information available, literally thousands of papers, and so in such systems you have a fairly good understanding of how GAGs bind proteins. But for most of the other proteins, I would say 99% of the proteins, we really don't know. Okay, what exactly are the molecular mechanisms or the structural basis, how they bind. Even if there is, we know something, there is no consensus. Okay. Yeah. Okay. For example, like the example I'm going to be choosing almost exclusively are going to be the chemokines. Okay. So the chemokines exist as monomer or dimer. Okay. And also I'll be talking about the GAG binding residues and the roles in affinity, specificity, geometry, and so on. All right, okay. So what are the challenges? All right, so once again, like this morning, we heard of a system which binds a pentasaccharide. Okay, but GAGs in reality, are much longer, and they're intrinsically heterogeneous. We heard quite a bit about this, and which also means if you want to study native interactions, you have to study with molecules which are intrinsically heterogeneous. Okay, so right away I can tell you, if there is heterogeneity, you cannot do biophysics. Okay, even to do a simplest binding interaction, like the examples which Umesh was talking about this morning, where A plus B giving AB a single complex. Under ideal conditions, you'll get the best results there are. Okay, but if you have one of the molecules which is intrinsically heterogeneous, which are intrinsically long, flexible, and the binding interactions, if it's intrinsically complex, on top of that, you have the limitations of the biophysical structural techniques, it's going to be extremely hard. Okay, so in fact, what the story I'm going to be telling you today are the message I want to press upon to all of you who are going to be working on, some aspect of GAG protein interactions, is that, okay, the devil is in the details. Okay, so we're going to be talking a lot of details today. Okay, so the system I'm going to be talking about is, leukocyte trafficking, and which I would have, like according to the original schedule, you have heard a lot more in detail about the biology and the immunology, but I'm going to skip that. Okay, so it's really not relevant to what I'm going to be talking about. Okay, all right. So with respect to the geometry of binding, okay, and stoichiometry and so on and so forth. So what I'm showing here is a chemokine. Okay, so the chemokine in principle can exist as a monomer or dimer. Okay, so you could have a monomer binding a single GAG. I'm showing a GAG as, like a wavy line, and a dimer can bind. So you have a simple 1:1 stoichiometry. Okay, this is the simplest case as it may be. But in reality, in vivo, you could have two GAGs, okay, as a proteoglycan. Okay, once again, Umesh talked about the avidity aspects. You could have a single chemokine binding to two GAGs, or like in this case a monomer binding, okay, two GAGs, a dimer binding two GAGs. Okay, here we have what is called a beads on a string model. Okay, you could have two chemokines binding a single GAG. Here you could have binding induced dimerization, and where the GAG actually binds like a horseshoe. Okay, that's called a horseshoe model. Okay, here you could have where the monomer initially binds, and on binding the dimerization occurs, okay, which is different from, okay, where a simple dimer binds, or where the two dimers on binding the GAG induce tetramerization, and where you could have a single GAG binding two GAGs and so on and so forth. Okay, so clearly I'm presenting all possible combinations of interactions which could occur in vivo, right? Because in vivo, we really don't know what's going on. So what do we mean by in vivo? In vivo, we're talking about proteoglycans, which are on the cell surface, and the chemokines are the ones which are, okay, in a nutshell, which are released, like for example in the lung, okay, because of tissue injury or whatever, they get into the blood, and from the blood, they recruit neutrophils in the reverse direction. And for the recruitment to occur, okay, so they have to bind to GAGs, okay, on the cell surface. They form a concentration gradient and so on and so forth. I'll be talking about a bit more in detail tomorrow. But in a nutshell, what the point I would like to emphasize is that the chemokines bind to GAGs. Okay, you could have both the monomer and the dimer binding to GAGs. Okay, and you could have the GAGs in the free form and the bond form and so on and so forth. Okay, so here we talked about different possible combination of chemokine GAG complexes. Okay, any questions so far? I'm trying to set up the picture of linking what could be happening in vivo and what you're going to measure in a test tube, right? When you measure affinity, what we measure is like in a test tube, in a cuvette as the case may be. Okay, but we want to make sense of what we measure in the lab to what could be happening in vivo. Okay, that's the link I'm trying to make in terms of giving all the background information. So far so good? Because this is important, okay, because from now on I'm going to be going into the details of the different techniques, okay. I really want to make sure everybody has an appreciation of once again what we are trying to go after and what is it at the end of the day we have accomplished so far. Okay, there's a huge, huge gap. I hope I'll be able to convince that. All right, okay, so we're done with this. Okay, so different biophysical techniques. Once again, Umesh did an excellent job this morning. Okay, so whenever any technique you're going to use, you're going to measure binding affinities. Simply speaking, KD. You briefly alluded to stoichiometry. Okay, I'll be talking about it a bit more in detail. We talked about kinetics and thermodynamics. Okay, and almost the same techniques we are also going to be using to describe the structural features, okay, and the molecular basis of the binding, okay, for example, the geometry of the binding, which residues involved in binding, and so on and so forth. Okay, so how many of you here have actually measured some kind of a binding constant from doing a lab experiment? None? Okay, it's actually a very small number. All right, okay. So how many of you are familiar from leading literature what a binding affinity is? Okay, so it's a really small number. Okay, all right. But all of you understand what we mean by binding affinity? Okay, so you understand what is strong binding, medium binding, weak binding, as the case may be. Okay. All right, so we're talking about a very basic fundamental property of a GAG or the protein, binding, right? Any of the biology is a consequence of the binding, how tightly it binds, where it binds, and so on and so forth. Okay, so we're going to talk about weak versus strong binding, and okay, now coming back to the technique, so let's see what I'm trying to get across in this chart. Okay, so what are the criteria, the variables we need to consider for measuring reliable, okay, I have that in inverted quotes, binding constant. Okay, the binding induced change in the signal, okay, like I know, like Umesh showed his data from fluorescence quenching, where you got very nice binding curves, okay, and I'm going to show you some cases where it's not that good. Should have a well-defined endpoint, okay, this is a very critical criterion, which once again I'll talk about. Interference from contamination, very critical for fluorescence-based experiments. Weak versus strong binding, apparent versus actual binding constant. Okay, this is once again Umesh in the morning was talking about in terms of affinity versus avidity. Okay, a lot of the literature they'll just talk about an affinity. Okay, so and in other words, so it's very critical we appreciate the difference between apparent and the actual binding constant. Okay, so in fact, in one of the summary charts which Umesh showed, actually which is Neha's review article, we saw a whole bunch of KDs, okay, but the KDs are not actual binding constant but apparent binding constant. For example, if they say nanomolar binding, so we would think it's tight binding, right? But it's tight binding only if it is an actual binding constant. If it's an apparent binding constant, it is a binding constant made of multiple binding constants. So it is an apparent binding constant. So conceptually, factually, apparent binding constants are very different from actual binding constants. Okay, and how sensitive the technique is. Okay, for example, a fluorescence by far and large can measure only a simple binding curve. I mean, if you try to fit the data, you always fit the data to a simplest model. But if the actual binding is complex, for example, AB2 rather than just forming an AB, you fit the data to AB, it gives you a good fit. You fit the data to AB2, it gives you a good fit. Okay, but the fact remains, if you can fit the data to the simplest model, you can fit the data only to the simplest model. So you cannot, the technique, most of the technique, especially fluorescence, is really not sensitive for measuring complex binding interactions. Okay, of course, there are some practicalities. We need large amounts of the protein or the GAG, the precipitation. Okay, it's a major issue for at least the systems we work with, the chemokines. You have time-dependent aggregations, okay, aggregation at higher concentration, okay, especially with respect to NMR. So this is something I'll be going to be talking about a bit more in detail. I'll answer a lot of these issues when I'm discussing the literature survey, okay. So the literature survey I'm going to be dealing with is when you read a paper, okay, any paper which involves protein-GAG interactions, and if the paper is to do with some aspect of binding, some aspect of affinity, using some kind of a biophysical technique, I hope from this class you get some kind of an appreciation of being critical of the data. Okay, in fact, the two of the papers I'm going to be talking about are 2012 papers which came out this year, and I hope to convey to you how bad the papers are. And the difficulty of the technique, and of course the availability of the instrumentation. All right, okay. So when we saw this list today, so there's a fluorescence, CD, steady equilibrium and velocity, ITC, SPR, NMR, crystallography, and animal model studies. Okay, so I'm going to be talking mostly about fluorescence and NMR. If time permits, at the end I'll be talking about the rest of the techniques. Okay, so some of the statements I'm making are very obvious, but I'll nevertheless go ahead and make it. All techniques cannot be used for measuring all binding constants. Okay, so that's something once again Umesh alluded to this morning. For example, if you're using fluorescence, most of the time your binding constants are like in the micromolar. Okay, but if your binding is extremely weak, it's like millimolar. Okay, or like picomolar, you really cannot use fluorescence. Okay, there's a concentration range over which a technique is sensitive. Okay, I'm showing it right here. That's what I'm saying, talking about that. And also if the binding is very strong, if it's nanomolar, you cannot use NMR or like ITC. In principle, it says you can use, but it's very hard to use ITC if the binding is extremely weak. Okay, so binding induced change in the observable. All right. I mean, once again, so what do I mean by it? Okay, so when A plus B is binding, you need to see a change in whatever technique you're using. For example, if you're using fluorescence, okay, you need to see a change in the intensity, either increased fluorescence or decreased fluorescence, okay. And another parameter which we use quite a bit in fluorescence is the wavelength, okay. So here I'm showing an example which has nothing to do with GAG binding, where where you can see you take a protein and you unfold it, and you can see where the initial wavelength is like 340 emission maximum, and if it's completely unfolded, it goes to like 352. So here is an example, okay, of binding-induced change in the fluorescence, okay, where there's quenching. And this is a paper which we'll discuss a lot more in detail this afternoon, okay. But it's a curve which we saw earlier. Umesh showed a similar curve, okay. And where this is a 16 more binding to a chemokine iolate, that's for the monomer, okay, and this is for the dimer, okay, all right. Okay, so as I said, I'm only talking, mostly about fluorescence and NMR. And fluorescence is by far and large the most popular technique which people use for studying any kind of interactions. I mean, if you can study by fluorescence, you prefer to do it because almost every single lab would have a fluorometer. If you don't have it, your neighbor will have it, and you take something, add something, see a change with the data, you get some numbers. Okay, that's how it is. I mean, for the papers I'm going to be talking about this afternoon, you're going to see that's exactly what we see. And so, it's simple, most commonly used. And so what are the caveats? Okay, most papers, most literature, especially if it deals with a new protein, they simply assume the stoichiometry is 1:1. Okay. And as I said, it cannot differentiate IR binding interactions, and a lot of the times they don't say it, but we need to appreciate that the binding constants are apparent and not actual binding constants, and often suffers from totally different endpoints. Okay, this is what I mean. Okay, so the authors basically assume that's the endpoint. Okay, but endpoint means it has to flatten out, and it's not flattening out; it is still going up. Okay, so we'll see why that is critical in terms of being able to get a quantitative KD. Okay, and this is something what we also discussed quite a bit in the morning is what is the readout? Okay, when you are looking at proteins, most of the time you're looking at tryptophans. Okay, so like in Umesh's case, there were 4 tryptophans, and because of the importance of the system, it's been very well studied. I guess people over the years have taken out 1 tryptophan at a time and measured to what extent each tryptophan contributes to the fluorescence and so on and so forth. Okay, so here is an example of system we study in our lab, interleukin 8, which has a single tryptophan. Okay, it's right there in the beginning of the helix, and we have all the lysines and the arginines, all over the protein. So when there's going to be GAG binding, okay, so you're going to see a change in the fluorescence, and that's exactly what we see. Okay, there's a quenching of this intensity of the tryptophan because of the involvement of these lysines and arginines. Okay, it's an empirical readout. That's all it is. Okay, we really don't know how exactly the tryptophan is, contributing towards the binding, but because of the binding, there's a change in its property, in this case the intensity, and we make use of that to measure a binding constant. So the assumption, okay, is that the change in intensity is proportional to the change in the increase in apparent binding constant. Okay, for example, the tryptophan is not in it's not in all the actual binding. Of course, if it was in all the actual binding process, that's a best case scenario. Okay, but in this case, it's sort of an indirect readout. Okay, all right. So I'm going to spend just a minute or two to actually go through the actual measurement of the KD. Right? I mean, this is something which I'm sure most of you would have seen in your freshman chemistry or in your graduate school, or maybe not. Okay, but of course, you read your kinetics, thermodynamics equations, do your exams, and then you forget about it. Okay, so this is how you basically get your KD. Okay, so and how to measure KD? There are 3 variables here, right? So A is changing, B is changing, and AB is changing. Okay, so to minimize the variables, you take the A total is A plus AB. You substitute. This is what you get. Okay, so what we have to remember is the B here is the free B, not the total B. Okay, and the equation which Umesh showed this morning was the total B. So when can we use total B in your math. Only time we can use total B in the math is if your A is much less than the KD. Okay, then your BT equals to B plus AB. No need to measure, we can just use BT. Okay, so it's an assumption where, for example, if the KD is like a micromolar, if your A, for example, enzyme A you're taking, it should be like a 0.1 micromolar, then you can assume your B is the same as B0, and which makes the math very simple. Okay, but so you cannot, every single case, just assume the BT equals to B naught. Okay, if your the binding constant is very similar to AT, like especially in the early points, a lot of the B goes into the binding, so your B0 is much lower than the BT. Okay. So once again, I'm going to spend a minute or two. Okay, like it's, I don't know how many of you have ever seen this kind of plots. Okay, so here I'm showing the fraction bound. Okay, this is a theoretical plot where okay, and also feel free to stop me if you don't understand anything, because the slides I'm showing here are very critical for the rest of the talk and for the discussion we're going to be having this afternoon. I'm basically giving you the ABCD of measuring binding constants. Okay, the theoretical, experimental, and the practical aspects. Okay, so the binding constant is 10 nanomolar. Okay, so like when it's like 10 nanomolar, you have, this is what I'm plotting is a free B. Okay, you have 50% of the B is in the bound form. You go up to 100 nanomolar, and what we have is about 90% of the B is in the bound form. Okay, here I'm plotting the same data in the log scale. Okay, so I'm just converting this data into the log scale. So you can see once again at 100 nanomolar we have 90% bound. But to go from 90% binding to 100% binding, you need 10-fold higher amount of free B. So if I plot this in a linear curve, this curve is going to go all into the next room. Okay? So this is 0 to 100, so 100 to 200, 200 to 300, 300 to 400. Okay? So this is a log scale. Okay? So to get 10% of the binding, you need a log unit higher. Okay? So most of the time, what we measure is about what we, ideally we need to get at least 2 log units, okay, where you can see starting from 10% of the binding and 90% of the binding, and the stuff it can be extrapolated. Okay, I'm basically showing the same data, okay, the same simulation, because I'm going to be showing some of these plots. So you can see like once again at 1 nanomolar, you have 50% bound, okay. This is in the log scale. And at 1 nanomolar, you have 50% bound, up like 10 micromolar, you have 90% bound. All right. Okay. Once again, coming to the technique. Okay, if I'm going to be using a technique which is not sensitive to measure binding in nanomolar concentration, so my KD is nanomolar, right? It's 1 nanomolar. Okay. Because like at 10 nanomolar, all the binding is all the binding is done. So because I can measure only at micromolar concentrations, what does it mean? I need to take more of the A and more of the B. So my B starts, okay, you can say like I start at a nanomolar and I'm going up to like 100 micromolar. So what's going to happen? Even after the first few points, all of it is going to be in the bound form. Right, because the actual binding constant is in the nanomolar, right? At like, you can see like at 10 micromolar, the binding is done. Okay, all of the binding is over. So I'm starting the binding under conditions where all of the binding is over. Okay, you can see that in the simulation, the KD is 1 nanomolar. Okay, but I'm taking so much of the B, so whatever B I'm taking, all the binding is done. Okay, so this is in the log scale and this is in the linear scale. Am I making sense? Is it clear? Feel free to ask me any questions, because this is something I'm trying to get across a point of the sensitivity of the technique. Okay, all techniques are not equal. All techniques are not equal. So let's consider the reverse case. Okay. the technique is not sensitive in the millimolar. For example, if your KD is 10 micromolar, okay, but it's good for nanomolar concentrations. For example, fluorescence anisotropy, okay, it's very good for measuring as anisotropy. So which means you're gonna, your B is going to be at very low concentrations, okay. So your binding constant is 10 micromolar, 50%. This is how an ideal. So in other words, the left and the right should match, okay. Your binding constant should be sensitive for a technique which is sensitive under the same experimental condition, okay. So if you use very low B, very total. Here I'm plotting the total B, and this is what is easier for us to visualize. You can see there's very little of the product formation formed. So you will not be able to measure a binding constant, okay. So what you're going to assume is that it doesn't bind. Actually, it binds in fact much, much tighter. You are just using a technique which is not sensitive for measuring very tight binding, okay. Any questions? Okay, so this is, in other words, this is the concentrations under which you should be working, but you choose a technique which is only sensitive under these concentrations, okay. Because if you go to a higher concentration, you're going to have, it won't work. You're going to have, like things which Umesh alluded to this morning. You're going to have photobleaching, you're going to have a PMT overflow. It just doesn't work, okay. Each technique has its limitations. Okay. So I was talking about fluorescence so far, okay, in terms of giving you an appreciation for measuring binding affinities. Okay, so now I'm going to be switching to NMR. Okay, so where it's a lot, the technique is a lot more powerful. Okay, so so what can we learn from NMR? Okay, so it's the only technique which can provide solution structure, okay, of a chemokine GAG or any protein GAG complex under native conditions. It's extremely versatile, provides residue-specific and atom-specific information, and in principle can provide insights into the molecular basis, geometry, affinity, specificity, stoichiometry, and so on. Most importantly, role of dynamics. All right, okay. So, I mean, this, as a person who does NMR for a living, what we are always excited about is dynamics. Okay, so as most of you know, GAGs are not rigid molecules. Or not any biomolecule is not rigid. They're extremely dynamic. The whole molecule rotates. Okay, like in the micromolar, nanomolar, time scales. Then you have the helices moving. Okay, then you have the breathing motions. Then you have the side chains rotating. You have single bonds rotating. So you have all kinds of motions happening within a biomolecule, okay, at time scales, like millisecond, microsecond, nanosecond, picosecond. And NMR is extremely powerful in studying these motions. And it turns out to understand the molecular mechanism, structure is just a place to start. Okay, a structure, especially a crystal structure, is a static structure, right? When you say structure, you're not seeing the atoms moving, but in reality, in solution, these molecules are undergoing all kinds of complex motions, and it's absolutely critical that we get some kind of a handle on these motions. Okay, people who do computational stuff, they do MD. Okay, you can from MD you get some kind of an insight into all this kind of different motion. But MD is very much limited to the time scale. Like on a good day in a good molecule can do like 10 nanoseconds, 20 nanoseconds. Okay, but if the molecule is very big, once again you're limited. But so it's not the same as getting experimental data. So NMR is very powerful with respect to that. So I'm not going to be talking about, and I'm not going to be showing any data at all with respect to the dynamics, but I want to make sure all of you appreciate the power of NMR. Okay. Of course, the challenges are with respect to anything we want to do. Okay, it's highly flexible, it's dynamic, and the binding interactions are weak. Okay, in fact. The point I would like to make is, contrary to what is generally alluded to in the literature, that the GAG binding proteins bind GAG with high affinity, I'm going to make a case that actually bind with weak affinity. And so in the sense, I'm going to differentiate avidity versus affinity. Okay, I think for me avidity could be higher, but it's not the same as affinity. The complex is often precipitate. In NMR intrinsically, we do need large amounts of proteins and GAGs. Requires fairly expensive instrumentation and requires a level of expertise. But the plus side is information content is very high. Okay, so one of the techniques I'm going to be talking about is called chemical shift perturbation. Okay, and I'll be showing some more data. Okay, so chemical shift. Okay, so how many of you don't understand the word chemical shift? Okay. So others have some kind of an idea what a chemical shift is? Okay, so a chemical shift is basically a property of the molecule. Okay, a property which is manifested when you put your sample in an NMR instrumentation. Okay, so the atoms which are magnetically active are the proton, nitrogen, and the carbon. Okay, the proton being the one H. For the nitrogen, it has to be N15, so we label it with growing the proteins in ammonium chloride, and C13 by growing the proteins C13 glucose. So basically what the chemical shift tells is it gives information of a specific atom of its environment. Okay, so whether it's in a part of a primary structure, secondary structure, tertiary structure, coordinate structure, what kind of interactions, and so on and so forth. It's extremely sensitive. Okay, so we will, just for today's class purposes, that's all we need to know. Okay, so with being sensitive, what happens is when there's binding, the chemical shift changes. Just like in fluorescence, we saw a change in the intensity, either decrease or the increase. When the binding happens, the chemical shift changes. Purely empirical. Okay, we'll see some spectra. The experiments are easily performed. It's simply, taking your protein and adding the GAG. So it's a very, conceptually, it's a very simple experiment. And most importantly, these days, we can do the experiment at concentrations as low as 10 micromolar, okay, which is 10, 15 years ago, you could not do such an experiment until you do the experiment. It's something like a millimolar, okay. So 10 micromolar is, is extremely low concentration. And so I'm going to show you data which shows the ability to do the experiments at low concentrations is absolutely critical for to be able to be successful in NMR experiments. Okay. Of course, the simplest. So what exactly have we learned is that in the case of GAG binding proteins, doesn't matter whichever protein, we do these kind of titrations and we can identify the GAG binding residues. So what's the caveat? Okay. Remember I said these are empirical, the chains are empirical, so which means it doesn't identify all of the binding residues and all of the perturbed residues may not be involved in direct binding, okay. So this is, this is a conversion from MAC to PC, so that's supposed to be an alpha, beta, gamma, delta, epsilon. Okay, so I'm showing you the lysine and this is the arginine, okay. So what in an NMR experiment we do is we look at the chemical shift of the backbone amide proton, but actual atoms which are involved in the binding are the side chains. In this case, the ammonium group, and in this case, guanidinium group. Okay, so we are talking about changes, 1, 2, 3, 4, 5, 5 to 6 bonds down the road, and still you will get information about the binding process. So far, so good.
So, what's the abundance of N15?
Sorry.
What is the abundance of N15?
Natural is 0.04%. 0.38, 0.4%.
It's higher than a carbon.
Carbon is 1.1. Carbon is 1.1.
So, how long do you have to run these experiments?
No, these are labeled. These are 100% labeled. Yeah. Okay, so because we are interested in the monomer dimer issue, I'll cut to the chase here. We have designed a monomer. Okay, so this is how a spectrum looks. Okay, so a chemokine, interleukin 8, has 72 amino acids. Okay, so this is a spectrum of the monomer. So the prolines will not give you a cross peak because the proline doesn't have the hydrogen attached to the nitrogen. So basically every cross peak corresponds to a signal from a specific amino acid. For example, this is from the lysine 15, valine 58, ALA 35, lysine 20, glutamine 8, and so on and so forth. Okay, so what we have is, when we are doing a quenching experiment, fluorescence quenching, we have one broad signal, right? Coming from whether 1 tryptophan or 27 tryptophan. So what you have was one peak. Now what we have here is 72 peaks, 72 signals, and which also gives you a residue-specific perturbation of what happens when the binding occurs. Okay, so let's see what happens. All right. Okay, so here I'm showing a spectrum, a series of spectra actually, of the dimer, which is the wild type, and of the monomer. Okay, so we start with the black. Okay, I can see that. Okay, with the black, which means I've just taken the protein and you start adding the GAG. In this case, it's an octosaccharide. As the binding occurs, the chemical shift changes. Okay, so which is what you see also in a quenching experiment. You see the intensity changes. But the only difference is, here we can look at the individual amino acid. Every single amino acid will respond depending upon the binding or not. For example, cysteine 7, no change. K3, no change. R6, very little change. R47 changes. C24 change. Doesn't change at all. Okay. We can get a residue-specific information. In other words, we are able to sample what's happening on the whole protein. Okay. This is for the dimer, and this is for the monomer. Okay. And from the from this kind of measurements, we can also measure binding affinities. Okay, so the dimer and the monomer have very similar binding affinities. Okay, and that's what you can see. You plot just like the way we plotted change in intensity of the fluorescence. What we are changing is the change in the chemical shift. Okay, but there you're going to plot only one, right? Because only tryptophan, for whether 4 or 6, we just have tryptophan fluorescence changing. But here I can plot many residues, right? Wherever there's a chemical shift, I can change. Change happens, I can plot, and you can see the binding is complete. Okay, it has a very good endpoint. That's what I mean by, okay, I can go ahead and continue, titrating, but this line is flat. It's not like going up. So I know I can rely on these measurements. Okay. So for the monomer, what I'm saying is the binding constant is 30 micromolar. Okay, all right. So here what I'm showing is I'm plotting the perturbation of each amino acid. How much is the perturbation as a function of amino acid? Okay, remember I said isolate has 72 amino acids. So I can plot what is the perturbation of 72 amino acids. Okay, and I also have, because I have the structure, I can give more information, okay? So what I'm showing in black are residues which are buried, okay? Meaning they are in the inside of the protein. So if a residue is in the inside of the protein, will it be actually involved in binding to the GAG binding? Yes, no, maybe, maybe not. Depending upon the face of the moon. It's in the inside of the protein, right? It's buried, okay? It's not accessible. If it's not accessible, this is my protein. Okay, I'm talking about a residue. Okay, let me give a specific example. Okay, this one, valine 61, right? It shows the highest perturbation, but in the structure, it's 100% buried. Okay, it's not exposed to the solvent at all. So if the GAG is binding, is a valine 61 involved in the actual binding process? Okay, I hear one person shaking their head. What about the others? Okay, it's who thinks here that it's involved in the actual binding process? Show of hands. Okay, so all of you think it's not involved in the actual binding process. Okay. So how do you explain such a large, in fact, shows the highest chemical shift perturbation? How do you explain that?
Change in conformation.
Exactly. Okay, so you can see the power of having the structure. Okay, putting the use of the structure to use. If not for the structure, the last thing you would expect is a buried residue showing a larger change in chemical shift, right? Because if something is binding, right, you think those residues should show the largest chemical shift change. But here you see, okay, valence external shows the largest changes. Okay, so okay, let's see the color code. Okay, so what we have, the line is basically the average chemical shift perturbation plus 1 standard deviation. So what we have done is residues which are above this line are residues which are involved in, one way or the other actually involved in the binding. Okay, residues which are in blue are all the lysine, arginine, and the histidine residues. Okay, residues which are commonly known to be involved in GAG binding. Okay, so here we start with lysine 3, arginine 6, K11, definitely not involved in binding, K15, histidine 18, K20, okay, is as an asterisk. Okay, it has an asterisk because the line completely broadens out. In NMR, when a line broadens out, implies, okay, it's very much involved in the binding. Okay, so let's not go into the details here. Okay, then we have K23, arginine 26, definitely not perturbed. K42, arginine 47, K54. Okay, so let's say that's your R60, a lot of perturbation. K64, 67 and 68. Okay. When we saw the results for the first time, we were absolutely surprised because K67 and R68, okay, which I'll talk a lot more in detail this afternoon, is very much involved in the binding process, but no perturbation. Okay, that's a caveat I said earlier. Okay, because there's no perturbation, doesn't mean it's not involved in binding. Something is involved. If you see a lot of perturbation, doesn't mean it's involved in binding. Okay, it's all context dependent. So that's for the dimer. This is for the monomer. Okay, so the same thing. You can see, the profiles are more or less similar, but there are differences. Okay, let's look at 68. Okay, very minimal perturbation. Okay, 68 is substantially perturbed in the monomer, and 68 is an arginine. And one thing I forgot to mention is in the structure, residue 66 to 67 to 72 is completely unstructured in the monomer. Okay, it's all over the map. Okay, it's free to move around. Whereas in the dimer, it's completely structured. Okay, so which means you would think something which is structured would interact much more nicely with the GAG, and what you see is that's not true. In fact, the unstructured monomer interacts much more tightly with the GAG than the dimer. So, I'm giving you a lot of the details, okay? I'm not interested in you guys remembering the details, but what I want you to appreciate is that this is a simple experiment, no different from your fluorescence titration, right? Okay, we're doing the same thing. We're taking some protein, adding your GAG. There you're measuring tryptophan, change in tryptophan intensity, but you're measuring a change in chemical shift of IL-8. Okay, that takes a couple of hours, it takes a day, it takes much longer, it takes more protein and so on and so forth, but the information content is much higher. You can talk about residue specific, that's a point I want to emphasize, how every single residue is binding or not binding, participating or not participating. For example, this, for example, in the monomer, the way it's unstructured, the very fact of seeing these large chemical shift changes implies it's on binding, these residues are becoming structured. Okay, so this is the aspect of getting into the molecular mechanisms of the binding process. Okay, so why is it all important? Okay, at the end of the day, especially all you medicine chemists, you want to design drugs. Okay, if you want to design drugs, it has to be high affinity, high specificity, and most importantly, what is very critical is the thermodynamic components to it, the enthalpy and the entropy. You want to maximize enthalpy, and at the same time you want to minimize unfavorable entropic interactions. Okay, so if something is unstructured and becomes structured, that is entropically not favorable. Okay, and that's in fact, Umesh gave excellent examples of loss of water, of a single loss of water molecule, which is very much an entropic phenomenon, results in orders of magnitude. Getting a micromolar binding is very easy, okay, but going to a nanomolar, which is what you need for clinical trials, is extremely hard, though it basically involves just 1 or 2 interactions, okay. To be able to design, to rationally conceptualize, okay, you can make use of this kind of information, structural information, okay. So there are 2 ways of doing drug design, okay. One is the rational drug design kind of things I'm talking about. The other one is high throughput screening, okay. In high throughput screening, you work in a black box. It's like, shooting in the dark. You shoot 1,000 bullets, you hope you hit the target. Right? There's really no science involved. It's purely technology driven, if I may. I'm sketching the concept here, but in principle, that's what it is. Okay. Here we are talking about first principles, right? Trying from first principles, trying to design something which where you can get what you're looking for. All right. Okay. So what was surprising for us? Okay, so now remember, like the molecule I'm talking about once again this afternoon and tomorrow is the best studied chemokine. Okay, so it is the
Your microphone.
Oh.
I don't know.
Oh, sorry. Okay. Look at it's about 20 years. The chemokine field itself is about 20 years old. It was the very first chemokine isolated, characterized, and very well studied. Okay, so this is the best studied chemokine. You would think we should know a lot. Okay, so I'm going to make a point how little we know. Okay, one of the surprises we found was K15. Okay, we found K15. K being a lysine, being substantially perturbed both in the monomer and the dimer. And there are, quite a few papers where people have tried to identify the dark binding residues in IL-8, and none of them identified a lysine. Okay, this lysine 15 as being important. Okay, so okay, so what we did was we went out and mutated the K15 to an ALA, and we did similar experiments, and we see that the ALA is not, it's not involved in the binding. We are plotting the difference in chemical shift, okay, and you can see there's a large change in the chemical shift, implying the lysine 15 is indeed involved in binding to the GAG. Okay, is everybody able to appreciate the point I just made? What's the big deal about? We are excited, but are you guys excited? So what's the big deal? So are you convinced that K15 is involved in GAG binding? Are the experiments showing that K15 is involved in GAG binding?
Cannot be true, right? Because it could undergo, it could be somewhere else, like the trailing tall people.
Okay, so what I'm plotting here, right, is a change in chemical shift of the lysine 15. Okay, and there's a large change in chemical shift. So the assumption is when you see a large change in chemical shift of a lysine or an arginine, okay, you expect it to be involved in the binding process. Or else would you explain a large change in chemical shift of a lysine and an arginine? Did someone say something? Okay, yeah, so of course the caveat here is, and I don't have a structure of the complex, right, to show the lysine 15 is involved in the actual binding process. Yeah, it is an empirical, at the end of the day it is still empirical. So, but it is a reasonable assumption that this lysine 15 is involved in the actual binding process. But to confirm if it is indeed involved in the binding process, the reason you do the mutation, if for some reason the position of the lysine 15 is involved in the binding, it shouldn't matter, right? Whether you put an ALA or some other residue, you should still see a large change in the shift, but it's not, okay? You don't see a change in the shift. It implies that the lysine 15 is indeed involved in the binding process. Okay, so because we have the structure, we can go back. And you can see that, so until now, the residues which were known to be important for function are these residues, 64, 60, 67, 18, 20, 68. Well, K15 is not somewhere over there. It is right there. Okay, it's right there in the same binding pocket. And so our data shows the binding involves not only these 6 residues, actually it also involves K15. Okay? And you can see, like, you can easily, the GAG can easily bind over here. Okay, so just showing the binding interface of both the monomer and the dimer. Okay, so I show the data for the octosaccharide. We didn't start with the octosaccharide. We have done the disaccharide, the tetrasaccharide, the octosaccharide, and actually we haven't done the titration for the 14-mer. If you were to go into the literature, if you're a person who does NMR or you work on chemokines, most of the papers, what the NMR data they would show would be for a disaccharide. Okay, and most of the papers will say that if they go to a longer oligosaccharide, the proteins precipitate. Okay. And we have gone up to 14-mer. 14-mer is, it's almost physiological. Okay, the 14-mer is like almost 3,000 a molecular weight. And I'm not going to go into the details here. Okay, I just want to emphasize, if you do the experiments correctly, you can measure binding of higher order oligos. Okay, so the trick to us was that we did all of our experiments using proteins at 50 to 100 micromolar. The islate when the NMR2 was 50 to 100 micromolar. And if you look at most of the NMR papers, they use a millimolar concentration. Okay, if you use a millimolar concentration, you add some GAG, it falls out of solution. Okay, so it's absolutely critical that you do these experiments at as low a concentration as possible. And another observation we made also was that the monomers will not precipitate, but the dimers will precipitate. Okay, so there is, yeah.
Does that also mean that the chains are binding multiple proteins?
That's a very good question. How do you study the molecular basis of something which falls out of solution? Only thing you know is you add, and it falls out of solution. Then you curse and, it's a very frustrating experience. Yeah, that's a very difficult question to answer, because one minute you have a nice clear solution, and what happens is you start adding your GAG, it'll be fine for the maybe first few titrations. Then you add, just like that, a solution will become cloudy and fall out of solution. So only thing you can do is you can speculate, right? It has to be some phenomenon happening at the molecular level. So it's very well established, from multiple methods, that GAG binding induces oligomerization. Okay, so it has to be some kind of oligomerization which is not kinetically regulated. So it's a phenomenon which is a runaway oligomerization. So now, of course, remember what happens when you're doing a GAG titration, right? It's charge neutralization. The chemokines are extremely highly positively charged. Its pI is like around 10. And of course, GAGs are the most negatively charged biomolecules on the face of the earth. Because during the titration, there's going to be charge neutralization. Okay, and also, and also the effects are very local. Okay, at local, when these things meet, okay, whatever is happening, if it's like an isoelectric point of the protein, it will just fall out of solution. Okay, maybe that's the reason if you keep the concentrations low, okay, but making this process unimolecular, right, you can extend the length of things like this happening. Of course, eventually a lot of this will fall out of solution. You keep it in the fridge, like in 4 degrees. You do the experiment like a month after. The solution may look clean, but you get garbage. Okay, so yeah, there's a point I emphasized right in the beginning of my talk. Okay? You're trying to study systems which are not easily tractable. It's a very difficult system to study. Okay, so that being the case, more informed you are in terms of what is that you are going after, better prepared you are in terms of being able to do experiments in a meaningful fashion. You just cannot take something, add something, and expect to get nice binding curves. Okay, so one thing we can see is that as you increase the size from a ditetract, the 14-month, the binding constants increases. Okay, we go from a, we couldn't measure at all for a disaccharide. It's more than 2 millimolar, but like a 150 micromolar, 50 micromolar, it is like 10 micromolar. It gets tighter and tighter. Okay, but once again, this is an apparent binding constant, because I'm assuming the stoichiometry is 1:1. I really don't know. We haven't measured the stoichiometry. Okay, that's something which we will do. But there's every reason to believe that the binding is 1:1. Okay. Okay, so I'm not going to go into the details, but I want all of you to appreciate that the binding curves are all very similar but not identical. Okay. And also the extent of the perturbation. Okay, I'm basically plotting the maximal perturbation, like 0.08, 0.2, 0.25. Okay, it all changes. And the perturbation is always higher for the monomer than for the dimer. Okay, like you can see goes up to 0.4, it's almost just a half here, 0.25, about 0.35. And I pointed the case of, the 67, 68. Okay, there are I'm not going to show you another docking. Clearly, the smaller saccharides have multiple binding surfaces. Okay, whereas as you go longer, it can only bind in a certain fashion. Of course, these are the ones which are more physiological. But the shorter ones are of interest for drug design. Okay, because you want the smaller one, the smaller the oligo, easiest to design. Wherever you put your sulfates, as the case may be. And these bind to, definitely define binding sites. It's not as if they're binding all over the place, because in every single case you see the perturbations are, is selective. Of course, as they become smaller, like the background sort of picks up because the signal is not tall enough. Any questions? All right. Okay. So my objective here is, not to teach you guys, chemical and biology, chemical and immunology, just to make a point of what we can learn from NMR. Okay, so the aspect of, for me, talking about NMR is to where we can get insights on the structural basis of the binding, but I also want to get across the molecular mechanisms of the binding, right? Okay, so how do chemokines recruit neutrophils? Okay, so remember I showed you a slide in the very beginning. Okay, they bind to gags on the endothelial cells. Okay, so the chemokines are presented to the receptors on the neutrophils. The receptors get activated. They get extravasated into the tissue. Okay, so it is commonly believed, it's almost a paradigm in the literature, that the role, it comes towards the role of the gag. Okay, so I'll be talking about a lot more in detail in tomorrow's lecture. Okay, one of the the theories is that the chemokine, the gag-bound chemokines are presented to the receptors on the neutrophils. In other words, it's the gag-bound chemokine which is important for the receptor function, because if it's not bound to the chemokine, if it's not bound to the gag, the chemokines free in the blood is going to get it's going to get washed away with the free flowing blood, right? So, and if there's no gradient formation, there's no recruitment. So it's very commonly believed that the presentation is critical. Okay, this is a gag-bound chemokine which is critical, and so what we were interested in finding out is whether it's true, right? Whether a gag-bound chemokine can bind to the receptor, right? So what we did, okay, we took the GAG bond complex, which is I'm showing you in the chemical shift. So this is the chemical shift of valine 41 when it's in the GAG bond form. This is the chemical shift of valine 41 if it's in the receptor bond form. So what we did was we took to this binary complex and started adding the receptor. Okay, because I'm not sure this soon. We already know which residues are important for receptor binding. There's there's no overlap. Okay, that's what was believed. There's no overlap between the receptor binding domain and the GAG binding domains. If that is the case, what should you see is you should see the chemical shift of this one going to somewhere else, right? Because it's a ternary formation of a ternary complex should be a sum of the two binary complexes, right? So you should see a shift of someone over there. What we saw in every single case was an averaging between the two binary complexes, meaning the isolate is either existing in the receptor bound form or the GAG bound form. Okay, there was no evidence in our experiments of a ternary complex. Okay. So once again, this is the power of an NMR. I'm just showing you three residues. We have plotted the chemical shift of every single residue. Okay, so the blacks are the extremes, whether it's in a GAG bound form or the receptor bound form. The blue circle is the experimental data, or the diamond is the theoretical data, where you can calculate if it's averaging between the two forms. And you see in every single case, the chemical shift we are observing is the average of the two forms. Okay, meaning the GAG bound form cannot bind the receptor and vice versa. Am I making sense? Indeed, you go to the structure, okay, and that's exactly what you see. Okay, so for the longest time, these residues we are known as involved in GAG binding, and H18 and K20 actually are being shown to be involved in GAG binding, but they are sort of peripheral residues, so it was sort of dismissed, right? So most people felt that the receptor binding and the GAG binding residues do not overlap, they're completely distinct domains. And you can see now that the K15, in fact, is right smack in the middle of the receptor binding domain. So there's substantial overlap between the GAG binding and the receptor binding residues. Okay, so once again I'm showing you the GAG, and this is the receptor binding residues. And the residues which are in the interface, which are involved both in the GAG and receptor binding, you can see it's right there, they're right smack in the middle. Okay, so this sort of summarizes what we've done so far. Okay, end loop residues, K15, H18, K20 are involved in GAG binding. So GAG bound chemokine cannot bind the receptor. Okay, so we propose recruitment is mediated by chemotactic and not aptotactic gradients. Aptotactic gradients means where the chemokine is bound in the GAG bound form. Okay, and if you have to read like a review article of how chemokines recruit leukocytes, and this will be the first sentences you'll see. Okay, it's aptotactic gradient is so well established. Okay, but what we are saying is that the recruitment is mediated by chemokine in the free form. Okay, so the bound form sort of regulates how much of the chemokine is in the free form, but the recruitment itself is mediated by the free form and not the bound form. Of course, these are mechanistic, but has profound implications of when you're thinking about designing drugs and where to target, when to target, how to target, and so on and so forth. Remember, devil is in the details. Okay, so completely switching gears. Okay, so now I went into the gory details of fluorescence and NMR. So now I'm going to spend the next 15-20 minutes talking about other techniques. Okay, the technique you want to use if you're interested in providing structural details is crystallography. Okay, almost all of coagulation literature and all of the serpent literature which Minister was talking about earlier this morning were all from crystal structures of these complexes. Okay, and the nice thing about crystallography is if you can get crystals that diffract well, it gives you residue-specific, atom-specific interactions in a single shot. Okay, I mean, you can get, in principle, this kind of data from NMR, but definitely not for large proteins like antithrombin. Like the chemokines are like 8 kilodaltons. They are like 100,000 molecular weight. So the information content is extremely high. Okay, because in a single experiment you get all of the structural information. The caveat, of course, is a lot of caveats. Remember, it's a static structure. Okay, because a crystal structure is always a place to start. It's not a means to end. Okay, a lot of the times. Okay, so I guess some of you have done crystallization. What do you do for doing a crystal structure is you set up a trial. Okay, set hundreds of different buffers, different precipitating agents, different pHs, whatever it is. Then you basically, pray and hope some of the crystals show up. Then you take those crystals. You don't care what pH it is, what ion extent it is. Okay, you then take it to a diffractometer. Then you see if it diffracts. Then you come with the structure. Okay, the details of the solution, the crystallization conditions are buried in the methods. Okay, you don't talk about what exactly the crystallization conditions are, but it may not mimic the native solution state. Okay, the solution state is pH 7.4. Like the PBS buffer. Okay, it's not 20% glycerol and 2 molar ammonium sulfate. Okay, so the crystallization conditions may not reflect anywhere close to solution state. And I'll give some examples. Okay, so at least for the chemokine complexes, only structures people have succeeded so far is a disaccharide. Okay, we go to a longer oligosaccharide, nothing happens. Once again, because gaps are heterogeneous. They're flexible for crystallization to occur. You have to dampen these motions. Okay, so you need these complexes have to be stable. Of course, you need large amounts of the protein. Okay, so I think the intrinsic heterogeneity and the flexibility limits the formation. And it's a hit and miss. Okay, unless and until it's a known system. Okay, if it's a new system, you just have to take the shot. And as I said, you set a lot of trials, and hopefully something will work. Okay, so there's concern with the potential artifacts. Okay, so here I give you 2 examples of what exists in the chemokine literature. Okay, so we have 2 structures, one of Rantus disaccharide and the STF1 disaccharide. I mean, I'm giving you a lot of the details. Okay, the bottom line is it's artifactual. Okay, I mean, there are some structures where you see some interactions could be native. There are other interactions which are like other biophysical measurements, mutagenesis have shown those interactions are not critical. Okay, are not involved in the binding. Okay. And so you're happy that you got a structure, but are the structures telling you anything at all about the physiological function? Okay, it doesn't. I mean, if you go look at these papers, it'll be like a 10-page paper, and they'll try to I don't know what happened there. They'll try to justify every single interaction as physiologically relevant, and it is not. Okay, they need to get a paper out of it, and you can see like interactions between subunits of the dimer and so on and so forth. And this is not only a problem for chemokine gas. This is a general problem of crystallography. Okay, the process of crystallization may result in non-native interactions. You may see the fact that 2 of them are forced together in space due to crystallization doesn't mean those interactions are physiologically relevant. But you don't know otherwise, so you assume that they are relevant. So, in fact, my conclusion is that, if anything, these studies emphasize we need longer oligosaccharides. Okay, whatever it takes to get the structure of a tetrasaccharide or octosaccharide or whatever it is. And even from NMR studies we saw that, right? Okay, ITC. All right, so what's great about ITC? Okay, so in addition to any technique, right? I mean, in a solution-based technique, one of the things you definitely get is binding affinity at KD. Nice thing about ITC is, in addition to that, it has a thermodynamics, okay, because what you're measuring during an ITC experiment is heat released. Okay. So that's directly proportional to, the KD and so on. And of course, without going to the math, because you can measure enthalpy, you can measure the entropy, and what is relevant for us as far as the protein-gas interactions is the stoichiometry. Okay, there is a technique which can give us the stoichiometry of the binding. And what is also useful is if you have structures or a model of the complex, and if you make mutations and measure the binding, you can get like residue-specific interactions. Okay, and I feel once again people are thinking about a career and designing drugs, which I think most of you are, and one way or the other. ITC is extremely powerful. Remember, always you want to optimize the enthalpy component of interactions and the entropy component of interactions. Okay. As I said, can give the stoichiometry, the gas size, so the different gas, and the heparin and heparin sulfate. Okay, so one of the caveats which we don't keep saying over and over again is most of the proteins bind heparin sulfate. Most of the literature is on heparin. Okay. And the reason is heparin is easily commercially available, right? Unlike heparin sulfate is not. Okay, so the caveat here is that the heparin sulfate has a structure NS, where NS is the sulfated part, is the non-sulfated part, and the gaps are like NS. Okay, and the caveat once again is that even in most of the proteins, in heparin sulfate, at least for chemokines, they bind to the NS. Okay, and also nice thing about ITC is no messing around, just adding A to B. You need a lot of the protein, you need a lot of the GAG. Okay. Because we need sufficient heat release. It does require expertise. It's going up. Just hold it in my hand. Okay. Look at some expertise, and precipitation could occur. Though it's experiment is like 60 minutes. Depending upon the GAG and the protein, precipitation is an issue always. Yeah.
So how much of the protein GAG do you need ITC?
Okay, so it all depends upon the signal. If you have a substantial heat release, you could get as low as 50 micromolar, but the cell volume is 1.4 ml. Okay, so it's quite a bit of volume, and you have to do a lot of control experiments. So it is. If you want to do ITC, a protein amount should not be limiting, especially if it's a new protein. You should be able to fiddle around. Okay, so here's an example of ITC study. Okay, we'll be talking about this paper this afternoon. See, 5 different commercially available heparins binding to wild-type islate, and the stoichiometry. Okay, for a molecular weight of 3,000, they get a N of 2 binding, meaning 2 islates binding per GAG. Okay, goes from 2 to 4, 5, 6, almost 12. And the KD. Okay, they measure a KD of 2 micromolar. Okay, it's give or take 2 micromolar. It's about 1 micromolar. Like for the longest one, it's a 0.4 micromolar. And of course, there's all this enthalpy entropy issue. So, and here the assumption. Once again, there are assumptions here. Though there are, for example, your 10, 12 chemokines binding per GAG, the assumption is all binding sites are equivalent. Okay, that's the assumption they make when they fit the data. In other words, there's no cooperativity in the binding. Okay, so they bind the data, they fit the data to a single binding site. So that is sort of the limit of this particular study. Okay, but this is the only study out there where it can give you the kind of information it does. Okay, I said in a single experiment you get for different GAGs, the stoichiometry, the affinities, and so on and so forth. Okay, beer core, quickly. SPR, surface plasmon resonance. Once again, Umesh went into a great detail about the experimental setup, okay, but I'm going to give you the bottom line. It's highly robust. You can simultaneously provide the K on, K off, the KD, and the stoichiometry of the binding, okay. Most of the literature doesn't discuss it, okay, but in principle, you can analyze the data to get the stoichiometry, okay. So this is critical for us. We can measure the binding under native conditions because the GAGs in vivo, the GAGs, the chemical binding to the GAGs is under native flow conditions, right? So in that sense, it's sort of native conditions. And also we can measure large GAGs. It's something which Umesh alluded to. You need less amount of the protein, the GAG or the protein, but if you're doing this experiment for the very first time, you have to do a number of control experiments, okay. In principle, you can characterize complex binding interactions, okay, including cooperative binding, okay. So most of the time, the data you get is an apparent binding, okay, at equilibrium just before the dissociation phase, or on the base of K on and K off. And as I said, you can also get the stoichiometry of the binding. Okay, so here is an example of a study where people have studied the binding of rantus to heparan. Okay, rantus is a chemokine. I'll spare you the details. Okay, so where from the nature of the binding, okay, they could fit the data to where they have two rantus dimers binding a single heparan. Okay, and also the binding is cooperative, meaning binding of one chemokine facilitates the binding of the second chemokine. Okay, but you can see, it involves quite a bit of math. Okay, the very last, this is ultracentrifugation. All of you use a centrifuge all the time, doing your protein preps and whatever it is. But there's a well-established technique in literature where, like using sedimentation equilibrium or velocity, you can measure the molecular weights of the different species in solution, which means you can also get the stoichiometry and the binding constants. Okay, it's robust, can be measured at different protein GAG ratios, and also can be used over a large concentration range. Okay, so that you can get a handle on what the binding constants are. And most of the time you're using the intrinsic tryptophan as a readout, but you can also use external chromophore. And I'll show you an example of where literature they have shown GAG-induced tetramer formation of a chemokine CP1. The limitations, because these experiments take a long time, the equilibrium, you do it like for 3 or 4 days, so it can precipitate, and you have to do the experiment at multiple ratios and rotor speeds so that you can get the stoichiometry. All right, so this is an example of binding of the wild type NCP1, which is a chemokine plus an octosaccharide. Okay, that's just the raw data, the residuals, where they're fitting the data to different models. Okay, ignore this data, where they're fitting here to a single species, okay, to a monomer dimer, equilibrium of the chemokine, here to a monomer dimer tetramer, and this is to a monomer tetramer. Okay, the best fit they're getting is to a monomer tetramer, showing binding induced tetramer formation of the chemokine. Okay, all right. So I've talked quite a bit. Hopefully that I've been able to get across some salient features of what one should expect and what one should know when you are trying to use a specific technique. Most importantly, if you are interested in measuring binding affinity for the very first time of any chemokine, any GAG, try to use a technique or use different techniques to get where you are spanning a large concentration range, and literally from picomolar to a millimolar, to get a qualitative KD, and then go after getting a quantitative KD. Whenever possible, get KD from 2 independent methods, okay, using different readouts like ITC and fluorescence, fluorescence and SPR or whatever it is, okay, because every single technique has the limitations, and if you can get very similar numbers from 2 different techniques, that very much validates what you want to say. Okay, so things like molecular mechanisms such as stoichiometry, cooperativity, and so on, always try to validate using different techniques. Appreciates the limit of different techniques. No technique is perfect. Understand the difference between apparent versus actual KD, macroscopic versus microscopic, avidity versus affinity. And that's it. So any questions?
You said that like XRD and like in XRD, it is not native conditions, so you can see protein-ligand interaction, which may not be in physiological conditions, like in XRD, right?
I'm sorry,
Like
XRD?
in X-ray crystallography.
Crystallography, yeah.
Do you know any example like where you can see this kind of interaction, protein-ligand interaction in crystal,
Yeah.
but not in NMR? Like in NMR, they don't show any interaction at all, whereas in X-ray crystallography, you can see interaction.
Right, yeah. Yeah, all the time.
So another question is it possible to measure this kind of interaction, like NMR, true NMR, in vivo? Like ligand?
In vivo, we still have a long way to. Okay, so the resolution, like any technique we have in vivo is like a micron, right? But these are like nano, we're talking 6 log units, right? But like a lot of the NMR they do is MRI, right? Magnetic resonance imaging, which is completely different. This is not at the protein level. You look at the relaxation of proton, carbon, phosphorus kind of thing. Yeah.
One small information. The new microcal ITC
Yeah.
can take only 250 microliters
That's
of
true.
protein with just 20 micromolar, and in the injection like 50 microliters.
That's true.
10 times much less than what conventional.
All right.